Hello, my name is Christopher Getschmann and I'm happy to talk about seed markers, shape-independent markers which are meant to be embedded in physical objects during manufacturing. Imagine a future where it may be common to own household goods that may be unique objects with customized or generated shapes and patterns. IKEA, for example, is marketing lampshades as unique one-off objects where the structure of no two lamps is identical. Design studios such as Nervous System create products with procedurally generated surfaces, 3D printed and made to order. Sometimes such generated elements in products are purely decorational, sometimes they are functional. However, while these are singular examples, having uniquely manufactured objects is already the case when we're talking about research situations. Tangibles are often created as one-of-a-kind objects with common rapid prototyping techniques such as 3D printing or laser cutting. At the same time, novel interaction techniques based on these objects often leverage some kind of optical detection or tracking to estimate the position or pose of objects. For this, usually computer vision markers are used. These are mainly squares or circles in shape, have a high contrast, and are mostly optimized for speed or robustness, with little regard for how they appear to human eyes. When placed on an object to enable interaction, they do not make use of the full size of the object and stand out, often looking strange and obtrusive. At the same time, when we are talking about rapid prototyped objects, there are several less obtrusive approaches to handle specifically these. There is GID, which allows to identify 3D printed objects based on surface artifacts. There is layer code, which allows an embedding of barcodes in layers of a print, or air code, which hides a QR code in air bubbles beneath the surface. But all of these approaches have in common that they only allow identification at a close distance, may require specialized cameras, and, with the exception of air code, they do not allow pose estimation. So, we want to tackle two problems at the same time. How can we design a marker that allows full pose recovery for complex interaction techniques, but that can be a part of a physical object manufactured with printers or laser cutters at the same time? Since these markers are supposed to be a permanent part of an object, it is beneficial if they would satisfy basic requirements in terms of aesthetics as well. To get an understanding on how common visual elements of computer vision markers are perceived, we did a short user study. We assume that markers either need to be aesthetically pleasing or at least unobtrusive to be accepted by people when it comes to placing them in their own home or their living spaces. We grouped markers by 5 common geometries or visual components and selected a representative marker for each group. We placed these markers directly on objects in a living room setting and showed these images to participants. They were asked to rate each one on a 10-point Likert scale how aesthetic, obtrusive or acceptable each marker is. Let's skip directly to the results. In total, 30 participants completed the survey. Metrics and color markers were rated most obtrusive. Several participants gave as a reasoning for their bad rating the similarity to QR codes. Markers that feature mostly organic shapes and especially circles were rated more favorably in terms of aesthetics, and overall the circle marker had the highest results for acceptance. The color marker, however, is a mixed bag, but was described especially as ugly by some participants. Take that with a grain of salt, but we can assume that smooth shapes are perceived better in general. But let's get back to the common markers for a moment. In order to encode information, most markers rely on position. However, if we don't rely on a fixed spatial encoding, we can fully utilize the full shape of a physical object and at the same time gain freedom in order to satisfy manufacturing constraints. This is the case when relying on the topological structure. If information is encoded as a sequence of regions, the regions itself can be of any shape and at any position as long as they represent the given topological graph. This is a technique that is used, for example, by DTouch and Reactive Vision's amoeba markers. However, we somehow need a way to generate a marker with a given topological structure that fits on our physical object and is suitable for manufacturing. The user study has shown that people rated circular and organic shapes as more aesthetic and acceptable. Manufacturing methods such as 3D printing or laser cutting benefit from curved or circular toolpaths with little or no 90-degree corners as well. To increase detection robustness and ensure manufacturability, structures need to be as large as possible. This helps generally in reducing the impact of imperfections from the manufacturing process. So, what we need basically is an optimal distribution. And we can have a look at how space optimization is solved in nature. When looking at sections of a fruit or fur patterns of animals or soap bubbles, certain visually appealing structures are reoccurring. This is often mathematically modeled with Voronoi diagrams. Voronoi cells are computed from a set of 2D points and are bound by the halfway distance to all neighboring cells. This applies well to situations with equal weights or pressures or distances. However, a simple Voronoi diagram is not suited to represent a large and possibly imbalanced topological graph. When adding an additional dimension, using a power function as a distance metric, we can extend this to the power-weighted Voronoi diagram, or short, a power diagram. In addition to that, when moving the point of each Voronoi cell closer to its center, we create a centroidal power diagram, which allows to iteratively optimize a set of 2D points. This works well for a wide range of complex geometries. But how can we manufacture this? Imagine you plan to design a small, tangible object. You might opt to 3D print that, and you will use a CAD program for design. You can export the drawing of the surface of the object, run the seed marker generator with the given shape, and re-import the generated marker as a technical drawing in your design. For 3D printing on a standard FDM printer, embossing the marker in the model works best. Then, after printing the first layer in one color, the filament can be changed and the marker is perfectly embedded in the resulting physical object. For laser cutters, simply engraving works best. This can be combined with removing pre-applied paint as well. In some cases, or prototypes may be too small to even have a casing, then the marker can be embedded directly in the circuit board. In this example, the marker regions work as capacitive touch buttons as well. In its default state, a detected marker yields only an ID and a 2D position in the camera image. React Division's topological markers offer 3 degrees of freedom by deriving an additional orientation vector from the position of nodes. This works well because it requires no prior knowledge. When full pose estimation is required, seed markers can provide up to 9 degrees of freedom, similar to common other computer vision markers. This is done by providing a geometrical information about the circles, which allows the detector to uniquely identify the position of at least 4 leaves of the topological graph. This allows pose estimation for large and complex markers, while smaller markers work well for simpler scenarios. Seed markers can be used as a drop-in replacement for existing React Division setups if necessary. In general, seed markers work well for a wide range of applications. Printed tangibles on classical tabletop setups are quite straightforward, but augmented reality applications are possible as well. But let's have a look at some technical aspects for a moment. The quality of pose estimation has been evaluated with artificial images compared to a commonly used marker. For images of the same physical size, a Ruko marker has better performance in absolute numbers right now. This can be explained with missing distortion corrections in the seed marker and a closer placement of point correspondences at the same physical size. But when comparing complex shapes, seed markers can span larger areas in general, resulting in a geometrical advantage compared to fixed shape markers. But seed markers have a distinct disadvantage. Due to relying on the topological structure, they have no error correction. If only a part of the marker is occluded, detection will fail. Another important point is that while generation works well for a multitude of shapes, generation will fail in certain cases depending on the shape or the topological structure. Because the Voronoi diagram is computed on the outer hull of the polygon, very concave shapes may result in issues, Very imbalanced graphs will result in non-optimal relative sizes, and odd shapes with narrow passages will terminate too early in the generation process. So, to conclude, seed markers are well suited for scenarios where an unobstructed view can be guaranteed. Large surfaces work especially well, and non-rectangular shapes are not an issue at all. At the same time, uncommon materials and objects can yield good results, and seed markers are very much suitable for all kinds of experimentation. Thank you for your attention.